Hello, welcome to Math 251, Calculus 1 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video we will take a quick overview of Chapter 3. Chapter 3 is all about derivatives, derivative rules, and shortcuts for derivatives. Well, we'll eventually get to that after we establish a few things. First of all, in the first section, 3.1, we will be redefining the tangent line problem and finding the derivative that way. And as you can see, there's going to be a couple of ways to find the derivative. We'll have two formulas involved, and this is looking for the derivative at a specific point. Now, once we establish the idea of finding the derivative at a specific point, we're going to look at the derivative as a function itself. So the derivative as a function will not plug in a value for a, but we'll look at the derivative of a function as another whole new function, where for each point we'll describe a slope. In this picture that you're seeing here, what we have is the original function f of x, which is the parabola, and its derivative is going to be this line, linear function. One of the things to look out for are when the original function has a zero slope, in this case the vertex of the parabola. That's when the derivative itself will be equal to zero, because remember, the derivative will be equivalent to the slope of the tangent line. After we do some of that, we're going to take a look at some derivative rules. So there's going to be derivatives of constants, the derivative of a sum or difference, and then when we get the derivative of products and quotients, it's not going to be as straightforward as the sum and differences. In these cases, we have a special rule that we need to employ when we're looking at derivatives of products and derivatives of quotients. And that is, for example here, looking at the product rule and the quotient rule. But once we establish some of these things, we're going to be able to take derivative shortcuts of a lot of things without having to use that original definition, which could be kind of tedious. In the next section, we're going to look at derivatives as rates of change. And so we can look at this in terms of velocity, and from the velocity, the rate of change of velocity is acceleration, so that would account for the second derivative. So that's probably, next to the tangent line problem, that's probably the next most common use of the derivative. But we can also apply this in economics as well, not just physics, but in econ, when we're looking at marginal costs. So if you have a cost function, the marginal cost is going to be given by the derivative of the cost function and how it's changing. And so there's a few other things that we can discuss when we see derivatives as rates of change of things that are happening in real life. In the next section, 3.5, we will be looking at derivatives of trig functions, and we will again employ the definition of the derivative with a limit, but once we have that, we'll use the derivative of these trig functions as formulas or shortcut formulas that we're going to try to remember. From here, the chain rule happens. So kind of along the lines of the product rule and the quotient rule, the chain rule is a way to take the derivative of compositions of functions. So when you have two functions that are composed within each other, we're going to have to use the chain rule to find its derivative. Just as an immediate application of the chain rule, we know that a composition of a function and its inverse will be the original input x, and so we'll use that idea to be able to find derivatives of inverse functions. So we can find the derivatives of x squared and x to the 1/2 power, as those are inverses of each other, using this, but this is more importantly used for finding the derivatives of things like your inverse trigonometric functions. And in a later section, we'll also be using this to find the derivatives of logarithms once we've established the derivatives of exponential functions. Another application to the chain rule is implicit differentiation. We're looking at derivatives of things that might not look like a function of x, like y is a function of x, but rather you have a relationship between x and y. And then if you're still interested in trying to find the derivative, or say the slope of the tangent line, in this particular example, we have what's called the folium of Descartes. And this is a loop that draws out clearly not a function not passing the vertical line test, but there is a relationship between x and y in this equation and in this graph. But as long as we know a point and we know the equation, we can still find the equation of the tangent line by using derivatives, or in this case implicit differentiation. And then finally, we're going to end with the derivatives of logarithms and exponents. And with these logarithms and exponents, we're going to come into a special technique that will help us find derivatives of complicated functions that are that have a lot of multiplying and dividing. Because if we know some properties of logarithms, we can change multiplication into addition, and we can change division into subtraction, and we know that we could take the derivatives of addition and subtraction a little bit easier than multiplying and dividing. So we could take advantage of this technique called logarithmic differentiation, where we would take the logarithm of an equation and then take the derivative of that implicitly, and then come out with a result. So this will also give us an opportunity to be able to find derivatives of functions where you have the variable in the base and the variable is also happening in the exponents. All right. So that wraps up our quick overview of Chapter 3. Chapter 3 is all about derivatives. After the first couple of sections, we're going to dive into some differentiation rules, and then we'll know them more as shortcuts to the derivatives. And from later classes, beyond Calculus 1, you'll just be using these shortcuts. Okay, I hope you're enjoying the class, and I wish you luck in tackling this chapter.